A student sets up the following electrochemical cell, and we've got cadmium and we've got tin in there. So let's just take a look. There's cadmium, and if I'm looking for tin, it's over there. So if I wanted a spontaneous reaction, I would be going backwards over cadmium and forwards over tin. So the cadmium, as it says here, solid becomes cadmium 2 plus, and tin 2 plus becomes tin metal. So which of the following statements is correct? The top one is always going to be my anode, and the lower one is going to be my cathode. So cadmium is going to be the anode, and tin is going to be the cathode. And what happens is cadmium is going to lose electrons, and electrons will flow from the anode to the cathode, and they will flow from cadmium to tin. Which means that if electrons are being attracted to the tin must be positively charged because it's attracting electrons. That electrode must be positive, and the cadmium electrode must be negative. So let's see what we can get out of this. So firstly, we know that that's anode and that's cathode. So cadmium is the cathode. No, it's not. It's the anode. Zinc is at least tin is the positive electrode. Ah, that looks like a very good answer. The electrons are flowing from the tin to the cadmium through the voltmeter. No, they are not. They are flowing from the cadmium to the tin. And electrons flow from the cadmium to the tin, yes. Through the salt bridge, no. It's through the voltmeter. The salt bridge does not transfer electrons. It transfers ions. Remember, electricity is the transfer of charged particles. Sacrificial anodes are used to protect metals that are oxidized easily. Which one of the following metals would protect iron from oxidation? So in other words, it has to be something that oxidizes more easily than iron. So it has to be above iron on the redox table. So the first thing to do is obviously to find iron. So we need iron 2 plus because you could use iron 2 plus or iron 3 plus. It doesn't really matter because they haven't been very clear. So there's the iron 2 plus, there's the iron 3 plus. Let's find the other guys in this little cast of characters. I'll make that a little bit bigger. And I'm going to find mercury. Mercury's all the way down here. So that's going to get reduced more easily, not good. And then we've got magnesium. Magnesium's all the way up here. That's a bit of this and a bit of that. Then we've got silver. Silver is nowhere to be found because it's even lower down. There we go. So there's my silver. And finally my copper, and my copper's over there. So what you can quite clearly see in this, what you can quite clearly see is that only one of the substances is above the iron. The other three are all below the iron, and so there's only one that would oxidize more easily than the iron, and that is your magnesium. If an electrochemical cell is based on the following spontaneous reaction, then the half cell where reduction occurs will contain what? So the first thing is quite obviously over here. We are going from magnesium to magnesium 2 plus. That's magnesium solid, that's the ion. And then we are going from Fe2 plus to Fe. And I could put the little S's in and all of that, but I don't have to when I'm just trying to work a multiple choice out. So then where reduction occurs, so I happen to know that I'll always write the anode, which is where the oxidation occurs. And then this is the cathode, and this is where the reduction occurs. And I can see that this became Mg to Mg2 plus, so that was quite clearly a loss of electrons. And so in terms of oil rig, that is my oxidation, because it was the loss of electrons. Just double check everything. You always write the anode first and then the cathode, because the letter A comes before the letter C. That's not the real reason, but that's what you'll remember. Okay, so what are we going to do? Then the half cell where reduction occurs, there it is iron and iron 2 plus. And you'll notice over here there was iron is just a single plus, but the sulfate ion is a 2 plus ion. At least a 2 minus ion, so the iron must be a 2 plus iron. So it is going to be B. The conversion of the dichromate ion to chromium 3 plus ion is a result of. So let's just look at this information over here. I'm going to find that particular half reaction. There it is on the periodic, at least on the redox table. And as you can see, dichromate, Cr2O7, becomes chromium 3+. And as you can see, I've written that forwards, which means that I've written it as a reduction. So that is a reduction. And people get confused because I'm going from 2- to 3+. And when I'm going from 2- to 3+, people start to think, oh, well, that must obviously be a loss of electrons and therefore it's oxidation. We are looking at this whole ion, but the oxygen doesn't change its oxidation state. Only the chromium changes its oxidation state. And if I were to put oxidation numbers on that, I would have -2 times 7, so it's -14. This would then, the whole thing has to be -2, so this would be +12, and that would be +6. So what has the chromium done? It has gone from being +6 to being +3, which is quite clearly a reduction. So the conversion is going to be a reduction, and reduction is always going to be from a gaining of electrons, so that's going to be A. Which of the following reactions can occur spontaneously under standard conditions? And so again, we're going to go through this table in technicolor detail, and we're going to see when I have got what above what. So, looking at a fresh redox table, the other one was looking a bit battered and bruised. I've linked my copper with my hydrogen over here, iron and copper, and I have linked iron and magnesium. This is garbage. It's 2+ and 2+ being added together, but there's no transfer of electrons that's going to occur from there. So I'm just going to eliminate D right from the very, very beginning. What I need is I need to get my C shape. So I need to be going from copper to hydrogen metal, but from the top to the bottom, whilst this goes from hydrogen backwards to copper in the end. So that doesn't work out. Ion metal becomes copper 2+. Yes, the iron metal reacts with the copper 2+ in a spontaneous reaction. That goes backwards and that goes forwards. Starting with iron metal, starting with copper 2+. And then if I try the other one, I start here with magnesium solid and iron 2+, not with iron and magnesium 2+. So the only spontaneous reaction over there is going to be your B. Consider the following two reactions. Real pain in the backside. You now need to assign oxidation numbers to all of those. If you've assigned all of your oxidation numbers, so here the sulfur is +4, sulfur is +4 because the oxygens are -2 each, and here your sulfur is -2, your magnesium is 0 because it's on its own. The sulfurs both turn out to be 0 because they're on their own. The water didn't change its oxidation state at all, it's still +1 and -2, and here your magnesium is going to be +2 because it's bonded to the oxygen, which is -2. So where did oxidation take place? Because remember, a reducing agent underwent oxidation. So it has gone from -2 to 0, and here from 0 to +2. So what were my two reducing agents? The hydrogen sulfide and the magnesium. Which of the following statements concerning this reaction is true? So we're going to go, you've got sulfur dioxide. Let's just look at our oxidation numbers again. And we land up with something that looks a little bit like this, where we've got oxidation over there with the magnesium and reduction with the sulfur. So it says, is sulfur is oxidized? Well, that would be going backwards, and this arrow is quite clearly going forwards. Sulfur dioxide is reduced. That looks like a beautiful answer, so we will just do that. The magnesium gains electrons. No, it actually loses electrons. And finally, both the magnesium and the sulfur dioxide are oxidized. No, they can't both be oxidized. One is oxidized and one is reduced. In the following reaction, which substance is the reducing agent? Again, you need to assign oxidation numbers to that, and you find that your oxidation is over here and your reduction is over there. So the reducing agent got oxidized, and that would be Fe2+. Then your next one, what will be formed when zinc powder is placed in an aqueous solution of copper? This is your classic Daniell cell. It's zinc metal becomes Zn2+. You could use the information sheet for this, but and then your copper 2+, copper sulfate, copper 2+ ion becomes copper metal. So what do you get out of it? You get Zn2+ and copper metal. Which one of the following ions is a stronger oxidizing agent than the H+ ion? And again, you're going to have to go to your redox table. So again, I'm just going to signpost all of them. This is the one that I'm comparing, hydrogen. And as you can see, 3 of them are above and 1 is below. So that pretty much tells you what the answer is. But let's think about it a bit more. Which one is a stronger oxidizing agent? So which one has the greatest oxidizing ability? The one lowest down, and that is copper, and it is below the hydrogen. The anode is always going to be the place where oxidation occurs. That's your definition of an anode. So let's not... You'll see it changes. Sometimes it's negative and sometimes it's positive, which is why I don't really emphasize that, depending on whether you've got an electrochemical or electrolytic cell. And then the standard conditions for a half cell, again, pure bookwork, and that is C, 25 degrees centigrade, 100 kilopascals, and 1 molar.